Hello and welcome to Mathemagica. Today we'll be discussing about the equation of a rotated ellipse. So, as we all know, when we are talking about an origin-centered ellipse on the xy plane, so this is the ellipse, this is my xy plane, this is A, this is B, and there is a point, let's say x comma y. So we can write the equation of this ellipse on the xy plane as x square by a square plus y square by b square equal to 1. Right? Now, let's say the same ellipse is rotated through an angle alpha such that this is your rotated system of axes such that this is x prime, this is y prime, and this angle of rotation is alpha, and the new rotated ellipse looks somewhat like this. What should be this equation of this rotated ellipse with respect to the xy plane? Now, one thing we can say for sure that with respect to the x dashed y dashed plane, the equation of this rotated ellipse is basically nothing but x prime squared by a square plus y prime squared by b squared equal to 1, right? We can write this. Now, today's discussion is about how can we represent or what would be the equation of this rotated ellipse in the xy plane. So, now we have this rotated ellipse and let's consider a point, let's say, which is x prime comma y prime with respect to the x prime y prime plane. What I mean by this is, let's say the distance of this point to the origin, let's say that's r, then if I drop a perpendicular on this, then this distance is my x prime, and if I drop perpendicular onto this y prime axis, then this is nothing but y prime and this is x prime. Clear? And let's say that the angle that x dash comma y dash makes with the x dashed axis, let's say that is nothing but theta. Okay, fine. So now again this x dashed y dashed, okay, with respect to x-axis and y-axis, let this be x comma y with respect to xy plane. Now what I mean by that is, if I drop a perpendicular here, right, then this is my x, and if I drop a perpendicular here, this length is my y. So I told you that in the x dashed y dashed plane, the equation of this ellipse would be nothing but x bar square by a square plus y bar square by b square equal to 1. Right? Now our duty is to find this x bar in terms of x and y, and this y bar also in terms of x and y. Right? So, from the diagram, we can conclude certain things like x bar equal to r cos theta and y bar equal to r sin theta. Right? Also, we can say from this very diagram that x equal to r cos theta plus alpha and y equal to r sin theta plus alpha. So, from these equations, we can write something like x bar equal to r cos theta plus alpha minus alpha, which is equal to, now here we apply trigonometric identities and we see that this is equal to basically r cos theta plus alpha, which is nothing but x into cos alpha. So x cos alpha, and here's a minus sign, but since it is cos, So here it would be plus r sine theta plus alpha, which is nothing but y and sine alpha. So this is your x bar, and y bar can also be written similarly like this: r sine theta plus alpha minus alpha. So y dash equal to r sine theta plus alpha, that is nothing but y cos alpha minus r cos theta plus alpha, which is x sine alpha. Clear? Now we put it in that equation where we wrote x bar whole square by a square plus y bar whole square by b square equal to 1, and we have x cos alpha plus y sine alpha by a whole square plus y cos alpha minus x sine alpha by b squared equal to 1. Right? Now, what we do is we rearrange this equation like this. So now we see that this equation can be written in this form: ax square plus bxy plus cy square equal to 1. Now, whenever we come across an equation which is of this form, ax square plus bxy plus cy square equal to 1, we can undoubtedly say that this is the equation of a rotated ellipse. Fine. In case of an ellipse which is not being rotated, its equation doesn't contain any coefficient of xy. But in a rotated ellipse, there is a coefficient of xy, right? So now, from this equation that we derived, we can write a equal to cos square alpha by a square plus sine square alpha by b square. We have b as sine 2 alpha into 1 by a squared minus 1 by b squared, and we have c equal to nothing but sine square alpha by a square plus cos square alpha by b square. Right? Now, we have to make use of these coefficients a, b, c properly so that we can derive an equation for this angle alpha in terms of a, b and c, right? So, what does happen when we subtract c from a? So, if we take 1 by a square common, then cos square alpha minus sine square alpha is nothing but cos 2 alpha. So, cos 2 alpha by a square minus 1 by b square. If we take it as common, then we have again cos squared alpha minus sine squared alpha, that is cos 2 alpha. So we can actually take cos 2 alpha common and write 1 by a square minus 1 by b square. Right? Now, if we divide this a minus c by, then we have a minus c by b. We have it as cos 2 alpha into 1 by a square minus 1 by b squared divided by sine 2 alpha into 1 by b square minus 1 by b squared. This part cancels out and we are left with cot 2 alpha, right? So we can further write alpha equal to nothing but 1 by 2 cot inverse of a minus c by b. So we found out the equation of the rotated ellipse, which was rotated through an angle alpha with respect to the xy axis, and also we found the angle alpha in terms of a, b and c. Now, my task for all of you is to find out the equation of an ellipse whose center was not at 0, 0, but at h, k, and now it is then rotated to an angle alpha. You'll observe that the equation is nothing but this. This is the equation that you will find out finally. Thank you for watching.